So let's now do a circuit example that brings everything together. The Kirchhoff's rules, the series and parallel resistors, and all of that. So here's an example. So one of the first things I want to say is, people often ask, how are the resistors connected? Are they in series or parallel? They don't have to be in either. You can have resistors connected which are neither in series nor in parallel. So in parallel, both ends have to be connected together. In series, they have to be end to end with no branching. You cannot have a third resistor button like this. The whole point of the series is that you have the same current going through all of the resistors. So if you have branching, that's not series. So it is possible to combine resistors in a manner that's neither series nor parallel. So just remember that. It doesn't have to be one or the other. And here's such an example. Look at this 10 ohm resistor. It is not in series with any of these other things over here. But if you look at also in terms of parallel connection, it's not in parallel with any other resistor either. You have to have both ends being connected to the both ends of the other resistor or resistor, then it's in parallel. So this is neither. So just remember that. So in some situation, you're forced to use the full Kirchhoff's rules to solve the thing. You cannot just use series and parallel. So now the first step in solving a circuit problem is label everything. Label the loops, label the junction, the resistors, and so on. And then that makes the thinking kind of much clearer and more straightforward. So here's a circuit all neatly labeled. So you have the 5 resistors, R1, R2, R3, R4, and R5. Then for the Kirchhoff's rules, you need junctions and loops. So this is going to be my loop 1 over here. This is going to be my loop 2 going around over here. Then the batteries are labeled with E1 and E2. So in some books, they use V battery or V sub bat for the battery voltage. In others, they use the script E. The script E, it stands for the electromotive force, or EMF. And that's because the battery is generating a voltage. So it's referred to as the electromotive force. And don't get bogged down in these terms. But the point is the battery's voltage is often denoted by a script E. So you have 2 batteries, so therefore this E1 and E2. And some books also just call it plain E instead of the script E. But that can get confused with the electric field. Now the next thing is, if you look at the resistors R4 and R5, they are in parallel. So you basically have 2 resistors like this. Both ends are connected together. Both ends are connected together. So for this, you don't have to worry about the Kirchhoff's rules at this point. You can simply combine them using the rule for parallel resistors. So you can collapse the 60s and 60s into a single parallel resistor whose value is 30 ohms. So let's see how. So for resistors in parallel, well, both ends are connected on both sides. The reciprocal of the total of the combination, that's equal to the sum of the reciprocals of each of them. So you have R4 and R5, so 1 over them equals 1 over the effective combined value. So this is 1 over 60 plus 1 over 60. This equals 1 over 30. So that's 1 over the total. So the total R4 plus R5 is 30 ohms. So this previous circuit that you have over here, it can be simplified. This second loop, you had 2 resistors here, R4, R5. Replace them with a single resistor R4 in parallel with R5, the combination, and that is 30 ohms. So here is the second loop. So this is this whole thing over here. This is loop 2. So let's now use Kirchhoff's rules to solve for these 2 loops and this junction over here. Okay, so here's how this works. So first of all, keep your eye on the price. We are asked to find the current I2 that's flowing through the 10 ohm resistor. So now there's not a direct way of finding that current using Ohm's law or series on parallel. So this is where the Kirchhoff's rules come in. So you solve for the voltages around this loop 1. You add these 4 voltages from the battery R1, R2, and battery 2 over here. The sum of those is equal to 0. You do the same for loop 2. So this whole thing is loop 2. Sum those voltages to 0. Then you go to a junction like junction 1 over here. these three currents add up to 0. So this gives you three equations. You have three unknowns, I1, I2, and I3. So you basically set up these equations and solve them simultaneously. So let's get started with the loop 1 over here. So here is the equation for loop 1. This is loop 1. You have to start at some point. So I'm going to start over here, the lower left corner. It doesn't matter where you start. You have to go back to that same point. Then you can go counterclockwise or you can go clockwise. So here I've just chosen to go clockwise. Also doesn't matter. You just have to choose it. So I'm going to start at this point and go clockwise. So first I have this battery E1. So that's my E1. I'm going from negative to positive. I'm going up in potential. So that's a plus E1. Here I'm going through this resistor R1. I'm going the same direction as the current. So you're going downstream. You're losing height. You're losing potential. So the value of this voltage, the magnitude is just the I times R. That is Ohm's law. So I1 and R1 over here, you have a minus because it's a drop in potential. You're going through a resistor in the direction of the current. So minus R1. Then you go to this resistor here, the 80 ohms. And that current is I3. So it's I3 times R2. Again, negative because you're going in the direction of the current. And then finally you go to this battery, except you're going backward. This is the positive end of the battery, by the way. So these big plates are positive, the small ones are negative. For the second battery, you're going from positive to negative. That's a drop in potential. So this battery is actually not providing power, it's getting charged, it's soaking up power. So regardless, as you go from plus to minus, that's a negative change in potential. So you have minus E2. And now you've completed the loop and come back to the starting point. So the loop is finished. This equals 0. So basically it's like going on a trail that's closed. You go up, you go down. If you come back to the same place, the visitor center, for example, you're at the same height. You're back to the same potential. That's what the Kirchhoff's loop rule is about. So now putting in the numbers, this is 9-volt battery, so plus 9. This current is not known, but the resistance is 50. So I times R is 50 times the I1 in this case. Similarly for the second one, I3 is not known, but the resistance is 80 ohms. So this I times the resistance, that's equal to the voltage. You still have the minus sign. And the second battery here, this is a 3-volt battery. So this is minus 3. It's kind of under this over here. There it is, 3 volts. Okay. So now simplifying this equation, I get an equation for I1. So I can solve for I1 in terms of I3. And here's that equation, just rearranging the previous one. So we are going to use this equation along with the other loop and the junction, solve it simultaneously. So label the equation. So these things that I draw, if I've not mentioned this before, the circle with the stick that looks like a lollipop, that's an equation label. So this is equation 1. So this completes the business for loop 1. Now we go to loop 2 and do the same process starting from this lower left corner. So you're going up this way, you're going against the direction of the current. So it's going to be a positive voltage change. When you're walking upstream, uphill, you have a gain in potential energy. So this is going to be I times 80. Then you're going through this one, same story. You're going downstream, so it's going to be minus 10 times I2. Then here, this was combined into a 30 ohm resistor, but you're going along the direction of the current. You're going downstream, so it's going to be a minus this I2 times this resistance, and then you complete this loop and you come back to the starting point. So here is what that equation looks like. So here it is. 80 times I3 positive because against the direction of the current. Then you go this way downstream, so it's minus 10 times I2, that's I2. Then you're going again downstream, so again it's minus, is the resistance, the 60s combined to give you a 30 times I2. The same current is flowing through this whole section over here. So that's I2, and now you're back to the starting point, so the loop is complete, and these three add up to give you 0. So rearranging this a little bit, I can solve for I2. That ends up becoming 2 times I3. So this is the second equation. So this has arisen from solving loop 2. So that now leaves the junction as the third equation. Once you have three equations, you have three unknowns, you solve them simultaneously. So this is the loop 2, and now let's do it as junction 1, this junction over here. So now we come to junction 1, this junction over here. So the junction rule is that all the currents entering the junction add up to 0, because what goes in must come out. There's no accumulation of charge. So here, looking at these currents, I1 is leaving, so it's minus I1. It's like if you take money out of a bank account, that's bad for the account. You end up with a lower balance. So you have a negative sign for anything that exits. You have a positive sign for anything that's entering. So that's I1. I3 is entering, so plus I3. I2 is also entering the junction here, so plus I2. So these three currents with their appropriate sign, they add up to 0, and this is Kirchhoff's junction rule. So let's label this as equation 3. Now you have three equations. It's a matter of solving for one thing, putting it into the other equation. You keep going until you solve for I2. So I2, remember the question was current in the 10 ohm resistor over here. So which is this I2 over here. So let's proceed solving the simultaneous equations. So equation 3 has three variables, I1, I3, and I2. So if you substitute equation 1 into equation 3, you can get rid of the I1. So that reduces it from 3 unknowns to 2 unknowns. So let's do that. Let's put this I1, this whole expression, in place of the I1 in equation 3. Upon doing that, you get this equation over here. So you get this equation over here. Let's rearrange this to solve for I3. So rearrange this and solve for I3. So that I3 ends up being 3 minus 25 I2 divided by 65. So now we have a connection between I3 and I2. Let's label this as equation 4. Now put this equation 4 back into equation 2. In equation 2, the end goal is to find I2, but I2 is connected to I3. So if you substitute equation 4, you'll get rid of the I3 in here. You'll have an equation only with I2, and then that can be solved to find I2. So put equation 4 into equation 2. Upon doing that, this is what you get. You have I2 equals 2I3, replace the I3 by the previous equation over here. You end up with the following. I2 equals 6 minus 50 I2 over 65. So sort of ignoring this middle thing over here, you have an equation with only I2. So solve for that I2. And upon doing that, you have the following. You have 65, bring this over here, bring the 65 up here. So you have 65 I2, bring the 50 to this side, so plus 50 I2. This is equal to 6. You're solving for I2. So I2 will then equal 6 divided by 115, which is a 65 plus 50. Now crunch this out. This gives you 0.052 amperes. So that's amperes in milliamperes multiplied by 1,000. That gives you 52 milliampere. And that's the answer to the whole problem. This is the current flowing through the 10 ohm resistor. So this is a good example that illustrates how we use Kirchhoff's rules, both the junction rule, the loop rule, and in combination with series and parallel. So at the very beginning, we use the simple parallel formula to get rid of the 260 ohm. We collapse them into a single 30 ohm. And so go through this on your own, see if you can solve it. If not, look at the solution one more time. But this should kind of prepare you for all kinds of problems in this category.